NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto is a distant and covert, more unassuming planet that was once a part of our nearby planetary assembly. However, evolving and controversial statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a staggering revelation. They suggested that this cold world is on a potential collision course with Neptune. But how could this really happen, and what might be the consequences of such a titanic event? Are we witnessing a perplexing cosmic anomaly, or is there something more to this impending celestial disaster? Join us as we explore the possible outcomes of a Pluto-Neptune impact. Pluto, once classified as a planet but later redefined as a dwarf planet, remains a subject of fascination in the vast universe. According to recent estimates by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potential catastrophic collision between these two celestial bodies, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it has yet to complete one full revolution. However, the intrigue does not stop there. Pluto's orbit is characterized by its unusually elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, tilted at 17 degrees relative to the ecliptic plane. The way Pluto moves along its path is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect based on their positions in the solar system. This naturally raises the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto stands out due to its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit, despite these complexities, is a testament to the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other through their gravitational forces. It's like trying to predict their future positions based on their initial locations and the way they pull on one another. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all interact in a highly intricate manner. The terms non-synchronous libration and orbital precession, along with the VZK oscillation, are key to this puzzle. According to astrophysicists, non-synchronous libration ensures that whenever Pluto crosses Neptune's orbit, it is positioned approximately 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from merging. Orbital precession, on the other hand, refers to the gradual shift in a celestial body's orbital orientation over time. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another key factor in this scenario is the VZK oscillation, named after three researchers, Vashkov, Zeldovich, and Kuznetsov, who studied how objects move in space. It describes how three celestial bodies like Pluto, Neptune, and the Sun exert gravitational influences on one another. This gravitational interaction affects how they move. In Pluto's case, the VZK oscillation helps explain why its orbit near the Sun is so irregular. Despite its seemingly unpredictable path, this oscillation helps maintain Pluto's stability over long periods. The VZK oscillation demonstrates that, although space may appear chaotic and unpredictable, certain patterns and gravitational forces keep everything in balance. These factors contribute to the stability of Pluto's orbit, preventing it from colliding with Neptune or drifting off course. This three-body problem is fundamental to understanding how planetary orbits evolve due to mutual gravitational influences. Studying it helps us learn more about Pluto, our solar system, and even distant exoplanets and their stars. Numerical simulations conducted in the late 1980s revealed that, despite its apparent stability, Pluto's orbit is actually chaotic over very long timescales. Even minor deviations in initial conditions can lead to significant changes over millennia. However, these peculiarities in Pluto's orbit have been found to maintain stability over exceptionally long periods. Recent computational models have been crucial in understanding how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune shares a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's immense gravity also plays a crucial role in stabilizing Pluto's trajectory. Saturn contributes as well. These studies indicate that Jupiter's gravitational pull is strong enough to ensure that Pluto remains on a consistent path for a very long time. In a way, Neptune, Jupiter, and Saturn work together to keep Pluto moving safely through space, avoiding potential collisions. These orbital intricacies are essential in maintaining order and stability in our solar system. Without these mechanisms, the solar system as we know it would be far more chaotic. Celestial bodies like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction of disruptions. For Pluto, particularly in discussions about a potential collision with Neptune in the distant future, understanding its orbit is crucial. It provides a clearer picture of the dynamic nature of our solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can reach a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and research to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange and unpredictable nature of celestial bodies. Pluto's orbit serves as a perfect example of orbital chaos, a concept that describes how small changes in initial conditions can drastically alter a celestial body's long-term trajectory. This is particularly evident in Pluto's case, where even slight variations in its position or velocity can significantly change its future orbit. Using advanced computational simulations has been invaluable for scientists in determining how Pluto moves through space. These simulations rely on sophisticated mathematical models to analyze how Pluto and other celestial objects, like Neptune, interact gravitationally. By adjusting small parameters in these simulations, astronomers can observe how even minor changes can dramatically impact Pluto's long-term trajectory. In the late 1980s, these models revealed fascinating insights into Pluto's orbital behavior. Despite having features like non-synchronous libration and other stabilizing factors, its long-term motion remains a subject of ongoing study. Orbital parade keeps Pluto's orbit stable, but its path can still be whimsical and unusual. Even a minuscule difference in Pluto's position or velocity can cause its orbit to look completely different after just a few years. However, despite this chaos, Pluto's orbit remains stable over extremely long periods. Billions of years. This essentially means that Pluto's journey around the Sun follows a certain order, even though it may appear chaotic at first. Predicting celestial events, especially when they involve unpredictable orbits like Pluto's, is a significant challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions, and even a small error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Additionally, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing, dynamic nature of the universe. While we have made tremendous progress in understanding space, Pluto's case reminds us of how much we still do not know. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly influence the stability and trajectory of other celestial bodies. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite the complex forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful views on the evolving nature of celestial mechanics and the public's interest in the overlooked realms of space. His position on Pluto's reclassification is based on our expanding knowledge of the solar system. He sees the reclassification not as a diminishment but as a significant change that aligns with our growing understanding of the many bodies orbiting the Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He views the complexities of orbits like Pluto's as a reminder of how much remains to be discovered in space. These questions keep space exploration so fascinating. However, despite Tyson's confidence, his concerns about Pluto's future orbit suggest that there may still be more mysteries to uncover. Will Pluto collide with Neptune, or is this just another moment of confusion in the ever-changing universe of space? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we still truly understand about our own solar system. We continue to study these celestial phenomena in hopes of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises another question about the mysterious and captivating universe in which we exist. The potential for such a collision challenges conventional understandings of planetary stability. The idea that two celestial bodies with such vastly different properties could collide is both unsettling and fascinating, especially considering the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and that Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be profound. Understanding the dynamics of a potential impact requires considering the structure and properties of both planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed primarily of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily composed of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would undoubtedly affect their structure and behavior, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly intriguing is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key component. Jupiter's immense mass, strong gravitational field, and gravitational momentum provide a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Furthermore, Saturn's gravitational influence adds another layer of complexity to the dynamics of the outer solar system, making it highly unlikely that a catastrophic event will occur between Pluto and Neptune. The ongoing study of Pluto and its relationship with Neptune provides invaluable insights into the nature of our solar system. Despite Pluto's reclassification as a dwarf planet, it continues to captivate the scientific community with its complex orbit and the potential for future changes in its trajectory. The gravitational interactions between Pluto, Neptune, and the other giant planets have long been a focal point for researchers attempting to understand the finer details of orbital dynamics. These interactions reveal the delicate balance that exists within our solar system, where even seemingly minor forces can have significant long-term effects on planetary trajectories. One crucial factor in studying Pluto's orbit is the role of resonance between Pluto and Neptune. As mentioned earlier, for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance is a rare phenomenon in the solar system, where 2 bodies' orbital periods are in a simple ratio, helping maintain stability between their orbits. This mutual relationship acts as a significant safeguard against potential collisions, ensuring that Pluto and Neptune never occupy the same region of space simultaneously. However, this resonance does not eliminate the possibility of disruptions from other forces, which could alter Pluto's orbit in the future. Another factor to consider when analyzing Pluto's future orbit is the influence of external forces beyond our solar system. While the gravitational pull of nearby planets like Jupiter and Saturn plays a significant role in stabilizing Pluto's orbit, the solar system is not a closed system. Other celestial bodies passing through the outskirts of our solar system could exert gravitational forces on the planets, including Pluto. These external influences, though rare, could cause shifts in Pluto's trajectory, potentially modifying its current orbit and leading to greater instability in the future. Furthermore, the study of Pluto and its eccentric orbit has broader implications for understanding planetary system evolution. By observing how Pluto interacts with Neptune and other planetary bodies, scientists can gain insights into how planetary systems form and evolve over time. These insights can inform our understanding of exoplanetary systems located far beyond our own, offering clues about how other star systems might develop and what kinds of interactions could occur between planets and other celestial bodies. The long-term stability of Pluto's orbit also ties into broader questions about the future of the solar system. While a Pluto-Neptune collision seems unlikely given current dynamics, it serves as a reminder that the solar system is constantly evolving. Planetary orbits, which may appear stable over human timescales, are subject to gradual changes over millions or billions of years. Understanding these processes enhances our knowledge of Pluto and helps us better understand the potential futures of the solar system as a whole, including the possibility of future planetary migrations or other significant changes to the structure of our cosmic neighborhood. These studies also emphasize the need for continued exploration and observation of distant regions in space. While much has been learned about Pluto, many mysteries remain, particularly regarding its internal structure and surface composition. Future missions, such as the continuation of the New Horizons spacecraft's journey through the outer solar system, will likely provide more data on Pluto and other distant bodies in the Kuiper Belt. This will enrich our understanding of this fascinating region of space and offer new insights into the complex interactions governing the movement of celestial bodies.